Across the quiet reaches of intergalactic space, where light travels for billions of years without striking a single grain of dust, an unfamiliar darkness drifts through the void. It is not the darkness of emptiness, nor the familiar silhouette of matter standing defiantly against the glow of distant galaxies. It is something far stranger, a shadow with no form, no substance, no visible source to anchor it in the known architecture of the cosmos. Here, in a region where galaxies thin into a pale scattering, astronomers trace the soft bending of ancient starlight. The gentle arcs and stretches of illumination reveal the invisible scaffolding of space-time itself. But then, amid the delicate curvature, a shape emerges. A contour of absence. A dark imprint that behaves like a shadow, yet belongs to nothing that any instrument can detect. It holds its outline with unsettling precision, as if cast by an object with sharp physical edges. Though no star burns nearby, no nebula clouds the view, no black hole warps the fabric with its hunger. It is a silent silhouette suspended in the cosmic sea, a contradiction etched into the universe's oldest light. In every corner of nature, shadows speak of presence. They reveal mountains at dusk, drifting worlds before their stars, the great invisible dance of planets and moons. But this shadow speaks of nothing at all. No mass. No radiation. No heat. Only the faint gravitational whisper of a shape that should not be. So the question rises like a cold tide against the boundaries of human understanding. What does it mean when the universe offers the outline of something that does not exist? And why does its darkness move? In the quiet hours before dawn at the European Space Agency's Deep Data Analysis Center, the great machines of cosmology continued their silent labor. Rows of servers whispered beneath cold fluorescent lights, converting raw starlight into meaning. Every night, vast streams of information flowed in from the Euclid telescope, a spacecraft designed to unravel the structures of dark energy and dark matter by mapping the subtle bending of light across billions of light years. Its mission, to reveal the unseen architecture of the universe through the delicate phenomenon known as weak gravitational lensing. Most of Euclid's data looked like gentle statistical noise, pattern distortions that only made sense through enormous averages and patient modeling. Astronomers sought faint shears in the fabric of distant galaxies, tiny stretches and compressions caused by invisible mass between Earth and the early universe. But on this particular week, the data was also being compared with parallel observations from the Vera C. Rubin Observatory in Chile, whose sweeping view of the southern sky captured nightly changes in cosmic structure with unprecedented precision. Together, these instruments were expected to refine humanity's measurements of dark matter halos, galaxy clusters, and cosmic webs. No one expected anything more than the usual complexities of lens reconstruction. No anomalies. No cosmic surprises. The anomaly appeared in the hands of someone who had no reason to be searching for it. Her name was Mara Kessler, a graduate intern assigned to a routine cross-validation task. She worked through the night, checking Euclid's lensing field maps against Rubin's multiband imaging. Her job was quiet, meticulous, almost invisible within the larger scientific effort. She sifted through color-coded diagrams of shear vectors, scanning for inconsistencies that might signal calibration problems or atmospheric interference. It was nearly 3 a.m. when she paused. One region of the lensing map, deep in the intergalactic desert between the Sculptor Group and the more distant Pisces, Cetus supercluster, showed a curvature that did not belong. At first, it seemed like a trivial misalignment, a lensing distortion too sharply defined, too coherent, too geometrically clean. Gravitational shear fields do not usually form perfect contours. They smear, ripple, or stretch gradually across the background of galaxies. But here, in a faint corner of Euclid's deep field, the distortion had a boundary, a distinct outline, as if the fabric of space-time were bending around the edge of something with a shape. Yet the region was empty, a void with almost no baryonic matter. No galaxies, no stars, no detectable clouds of molecular gas. And according to Rubin's optical data, no mass concentration bright or dark existed there. Mara zoomed in, expecting the familiar artifacts of faulty reconstruction. Pixel misreads, sensor ghosting, Improper noise subtraction. Weak lensing maps were notorious for false edges. But the outline remained. Not fuzzy, not drifting, but precise. A gravitational imprint carved into light that had traveled billions of years. It resembled, impossibly, the profile of a shadow. She marked the anomaly and ran the standard error diagnostics. Nothing flagged. The pipeline validated the result. The curvature values, the deformation matrix, the lens plane equations, all returned results consistent with real lensing. It made no sense. By morning, the senior cosmologists gathered around her terminal. Their voices stayed low, their thinking quiet and methodical. The anomaly was not dismissed, but neither was it embraced. It became the subject of controlled skepticism, the first instinct of any scientist trained to distrust miracles. Dr. Lien Ortega, the lensing specialist overseeing the Euclid data stream, requested a full reconstruction using independent reduction pipelines. 3 separate algorithms processed the same region using entirely different mathematical approaches. Each one returned the same unmistakable signature, a lensing contour with no associated mass density. On the Rubin side, the skepticism only deepened. The observatory's deep optical scans revealed no overdensity, no faint dwarf galaxy, no ultra-diffuse structure. Nothing. Even when they pushed the detection limits to the edge of noise, the region remained pristinely empty. The anomaly had shape, but it had no substance. Some considered the possibility of a foreground object drifting across multiple exposures, perhaps a nearby dark asteroid or a rogue interstellar remnant blocking starlight. But lensing cannot be produced by mere obscuration. It requires mass, gravity, energy, something capable of bending the fabric of spacetime. And the anomaly bent the fabric. Gently, subtly, but undeniably. Within days, the investigation expanded. X-ray overlays from NASA's Chandra Observatory were examined. They showed no hot gas or compact object. Infrared data from WISE revealed no warmth, no faint brown dwarf, no distant star cloaked in dust. Radio data from ALMA detected no emission of any kind. Every catalog declared the same verdict. There was nothing there. Yet the universe behaved as though something were present, something that forced ancient photons to shift their trajectories, bending around an invisible form. The anomaly was assigned a temporary designation, lensing object candidate 0x1. A placeholder, because none of the researchers believed it was an object at all. It did not behave like any known entity in astrophysics. It had no gravitational mass associated with it. No halo. No dark matter clumps sculpting the curvature. It was pure geometry without substance. A shadow without a source. At a closed-door meeting that week, the team reviewed the time-ordered sequence of observations. Even more unsettling patterns emerged. Rubin's dynamic sky scans, which captured changes night after night, showed that the lensing outline shifted very slightly over time. Not randomly. Not chaotically. But with a drift barely perceptible, almost like a slow migration across intergalactic space. If this were a dark matter clump, it would have shown up in mass integration maps. If it were a rogue black hole, it would emit gravitational curvature thousands of times stronger. If it were a primordial black hole, its mass would still glow faintly in Hawking radiation signatures or at least appear in CMB residual maps. But it was none of these things. The team debated simulations from Lambda CDM cosmology, asking whether exotic cold dark matter could form an invisible filament or shell with such properties. The models failed. Structures of dark matter, even at their most tenuous, still correspond to measurable potential wells. But here, the gravitational potential was effectively zero, yet the lensing effect remained. It was as though gravity were bending around the boundary of something that had no gravitational mass at all. A hypothesis emerged, whispered almost with reluctance. Perhaps the anomaly was not an object, but a tear, a discontinuity in the space-time field. A region where the metric tensor behaved differently, bending light not through mass but through geometry itself. Such ideas had been debated in speculative literature, wormhole throats, vacuum domain walls, or defects left behind from early cosmic inflation, but none had ever been observed. These were possibilities that belonged more to theory than reality. And yet the data persisted. More tests followed. More reconstructions. More attempts to disprove it. But with each step, the anomaly became more real, more undeniable, more unsettling. At the center of the investigation, Mara found herself swept into a growing collaboration spanning 3 continents. Her late-night curiosity had revealed something the universe had hidden with immaculate silence. The discovery ignited a quiet urgency, a sense that they were touching the outline of a phenomenon the cosmos was not yet prepared to reveal. No one knew what the anomaly was, but everyone understood what it was not. It was not a galaxy, not a cloud, not a star, not a black hole, not dark matter, not an instrument glitch, not a software error, not an illusion of the telescopes or the analysts who interpreted them. It was something entirely outside the catalog of cosmic structures. A boundary where none should exist. A silhouette of the impossible. A shadow in a place where nothing cast it. And as the discovery phase closed, one truth settled over the scientific community with the quiet weight of a dawning storm. They were witnessing the first shape of a mystery that did not belong to any known universe of explanations. A darkness that hinted at something waiting behind the fabric of reality itself. Across the global astronomy community, the anomaly spread like a ripple sliding through still water, quiet at first, then growing, gathering weight, disturbing the surface of long-held certainty. It began with private messages between research groups, cautious exchanges of raw data files, and late-night video calls where seasoned physicists stared at their screens with the same expression, disbelief tempered by the fear that the universe had just broken one of its own rules. Because what Euclid and Rubin had uncovered was not merely unexpected. It was impossible. For more than a century, physics has held to one unbroken principle. Shadows do not exist without something to cast them. Light bends only when something, mass, energy, or curvature generated by them, stands in its path. In the language of general relativity, mass tells spacetime how to curve, and spacetime tells light how to move. Every gravitational lens, from immense galaxy clusters to hypothetical primordial black holes, begins with this simple exchange. But the anomaly defied it completely. Scientists found themselves facing a contour of lensing without the mass that should have created it. Light from distant galaxies flowed around a boundary in the void, as if skirting the shape of an object that simply was not there. No radiation leaked from it. No particles drifted through it. No heat signatures, no spectral fingerprints, no gravitational potential wells. Every observational channel returned the same verdict: absolute absence. It behaved like the inverse of a black hole, a structure that shaped spacetime without containing any form of matter or energy. This was where the true shock began. Black holes, the most extreme gravitational phenomena known, curve spacetime because they compress mass into a region so dense that escape becomes impossible. Even they obey the rule: mass first, curvature second. Singularities may stretch the limits of physics, but they do not violate the foundation that curvature emerges from mass energy. Yet here stood an outline of curvature with no singularity, no mass, not even a whisper of gravitational influence detectable through conventional metrics. The earliest reaction was denial, not emotional, but methodological. The community did what scientists are trained to do: assume the instruments were wrong. Lensing reconstructions can be fragile. Errors can arise from miscalibrated optical elements, statistical noise, or even varying temperatures inside the detectors. Euclid's engineers rechecked thermal stability logs. Rubin's optical systems were scrutinized for distortion. Calibration stars were reanalyzed, and atmospheric interference models were rebuilt from scratch. Everything came back clean. The shock deepened when theorists entered the discussion. They combed through the mathematics of general relativity, searching for a loophole. None was found. Einstein's field equations described the geometry of spacetime as inseparable from the energy and momentum it contains. To produce curvature without mass would require a fundamental rewriting of the most tested theory in modern physics. A theory validated to extraordinary precision, from Mercury's orbit to gravitational waves detected by LIGO. And yet the data insisted that something was bending light precisely as if a massive object were present, though the object itself had no mass at all. The difficulty was not that the phenomenon contradicted general relativity. It was that it contradicted the very idea of cause and effect in gravitational physics. If curvature could exist without mass, then the universe might host structures governed by rules entirely separate from the observable cosmos, shapes born not from matter but from geometry alone. At conferences, physicists gathered in hushed clusters, staring at projected lensing diagrams that resembled the silhouette of an invisible form. The images were unsettling, perfectly edged distortions, like a shadow burned into the cosmic background. Cosmologists accustomed to dark matter halos and gravitational wells struggled to articulate the unease they felt. Dark matter was invisible, but it still produced measurable mass. It moved, interacted gravitationally, and shaped the galaxies themselves. But this was emptiness pretending to be mass, a vacant region bending light for reasons that made no physical sense. In internal memos, some researchers compared the anomaly to a massless gravitational imprint. Others described it as curvature without a source. The most unsettling description, whispered only in late-night discussions, called it a missing object, as though the universe were showing the outline of something erased. Emotionally, the scientific shock ran deeper than the data suggested. For decades, cosmology had embraced the unknown, dark matter, dark energy, inflationary fluctuations, the cosmic web, all mysteries that, while incomplete, followed the rhythms of established physics. They were puzzles waiting for pieces. But this anomaly was not a puzzle missing a piece, it was a shape that did not belong in the puzzle at all. Astrophysicists described a strange mixture of dread and awe, a sensation that the cosmos had revealed something it was not meant to. The more they studied the anomaly, the more it resembled a contradiction emerging from the darkness, a quiet violation of the universe's most sacred symmetry. At several institutions, emergency seminars were held. The questions asked were unnerving. How can curvature exist without a gravitational source? Why does weak lensing detect an outline that mass mapping algorithms do not? Could this be evidence of exotic spacetime defects predicted by inflationary theory? Is the anomaly static, or does its slow drift indicate dynamics beyond known physics? Are there other shadows like this hidden in the sky, unnoticed until now? These questions were not asked lightly. Each one attacked the foundations of cosmic structure. If this anomaly were real, then mass was no longer the sole sculptor of spacetime. The universe might be capable of forming shapes built entirely from geometry, as though some deeper layer of reality were poking through the observable cosmos. As weeks passed, the emotional toll on the scientific community became tangible. Astronomers accustomed to dealing with the unimaginable felt a growing weight, a sense of being watched by something unseen, something that left contours in the fabric of the universe but not the substance that should accompany them. One researcher described the experience in an internal report. It feels as though we are studying the shadow of an idea instead of a physical object. Another wrote, "The laws we trusted do not know what to do with this." The shock culminated when a comparative analysis was released. Using data from gravitational lens modeling, a team reconstructed the precise geometry of the anomaly. What emerged was unmistakable. The contour was intentional, not random. Its boundaries were too clean, too stable. It appeared to curve light with a consistency resembling manufactured structure, though no known natural or artificial object could exist there. This was the moment the scientific world collectively exhaled. Something was bending the light of distant galaxies. Something shaped like an object yet containing no object. Something that behaved like the universe's own contradiction. The anomaly had forced humanity into a confrontation it had never prepared for. The realization that the cosmos might contain forms that do not obey the rules of matter, energy, or even conventional spacetime. Forms that cast shadows without existing in the way anything is known to exist. And in that moment, the scientific shock transformed into something deeper, something heavier, the quiet understanding that this discovery would not merely challenge cosmology. It would redefine it. In the months that followed the first detection, the anomaly refused to fade from the scientific imagination. It hovered at the edge of verified reality, a distortion without shape, a shadow without a source. And so the investigation deepened. Teams across 3 continents coordinated their instruments, turning the full power of modern astronomy toward the faint pattern carved into the fabric of space. The first to return new data was the James Webb Space Telescope. Suspended in the cold stillness beyond the moon, Webb drifted in its halo orbit like a silent sentinel, its gold mirrors drinking in wavelengths too delicate for human eyes. When engineers commanded it to focus on the coordinates of the anomaly, the telescope responded with a clarity unmatched by any instrument before it. What Webb saw was nothing. Not an object, not a cloud, not a stream of matter or a hidden galaxy. Yet the void it observed was not empty. Light bent around the region in a way that mimicked gravitational lensing, except there was no mass to cause it. It was lensing without a lens. A shadow cast by an absence. Webb spectrometers traced the background infrared signature and reported a subtle curvature, a smooth, deliberate distortion carved into the quiet backdrop of the cosmos. It was perfectly consistent with earlier detections, as if the universe itself had drawn the same shape across multiple wavelengths. Then came Chandra. Orbiting much closer to Earth, the Chandra X-ray Observatory offered a different perspective. X-rays do not behave like the softer light Webb studies. They reveal the most violent regions of the cosmos, collapsed stars, jets from supermassive black holes, the torn surfaces of neutron stars. And yet Chandra, when pointed at the same coordinates, found something paradoxical, an X-ray void shaped exactly like Webb's infrared distortion. Yet this void was not a darkness of absorption. It was a darkness of displacement. X-ray background counts dipped along the same contour Webb had drawn, as if high-energy particles were being subtly nudged aside. Once again, no object was present. Nothing blocked the path of the photons. But something shaped them. ALMA in Chile provided the third perspective, observing in millimeter wavelengths, the frequencies of cold dust, quiet gas, and ancient cosmic background relics. If the anomaly was a cloud of molecular material, ALMA would have revealed it instantly. But the array's interferometric mosaic returned the same impossible outline, a distortion etched into the sky like the negative of a gravitational fingerprint. 3 instruments, 3 wavelengths, 1 identical shape, and yet no mass, no visible cause. No gravitational signature strong enough to account for the warping. It was as if the universe were folding around a memory, something that once existed but no longer did, leaving only its outline pressed into spacetime. Scientists began assembling the datasets into a layered map. Each telescope had captured the distortion from a different angle, and when combined, the overlapping contours aligned with unnerving perfection. The region behaved almost like a projection onto space-time itself, a faint bruise on the cosmic skin. The next step was redshift analysis. By studying how light stretched as it passed near the distortion, cosmologists hoped to determine whether the anomaly lay in the foreground or was imprinted onto distant background light. Webb's deep field spectroscopy measured the redshift of galaxies seen behind the distortion. Their spectral lines were subtly displaced, the shift was small, but consistent across the entire outline. Light skimming the anomaly appeared to undergo a uniform shift, as though it passed through a region where space-time was pulled tauter than usual. But again, the numbers told another strange truth. The shift did not match gravitational warping. Gravitational lensing should vary with angle and distance. But here, the effect was perfectly even, as if the distortion were a flat imprint rather than a 3-dimensional curvature. And this led to an even deeper mystery. When the cosmic microwave background, the universe's oldest light, was mapped across the same region, faint echoes appeared along the edges of the distortion. These echoes were not images, but statistical anomalies, tiny temperature variations vanishingly small, yet unmistakably correlated with the boundary of the outline. At first, the anomalies were dismissed as noise. But after repeated measurements, their alignment proved too precise to ignore. The CMB ripples hinted at something interacting with the earliest fabric of space-time, not an object interfering with today's universe, but perhaps a remnant effect imprinted billions of years ago. The edge of the anomaly seemed to whisper with echoes from the dawn of structure itself. Physicists turned to quantum field simulations to explain it. If the anomaly was not made of matter, could it be a drop in the density of vacuum energy? Could quantum fields fluctuate in a shape so stable and so large? Models were constructed using the known dynamics of the quantum vacuum, the restless, seething sea beneath all of reality. Most fluctuations appear at subatomic scales, flickering into and out of existence in a heartbeat. But under extreme conditions, such as inflation, cosmic strings, or domain walls formed in early phase transitions, larger signatures could persist. The simulations revealed something unexpected. Along the exact contour of the distortion, the vacuum energy behaved irregularly. Test particles in the simulation experienced microvariations in virtual particle density, as if the quantum fields themselves were being stretched. These microfluctuations resembled instabilities seen only in theoretical scenarios, particularly in models describing topological defects, relics of the early universe that never quite formed, or that formed only partially, leaving scars in spacetime rather than physical structures. If the anomaly was such a scar, its shadow-like form might make sense. It would not contain mass. It would not emit radiation. It would simply be a region where the fabric of reality had been forced into an unnatural configuration long ago, leaving only the memory of tension along its edges. And yet even this explanation seemed incomplete. For when scientists zoomed into the boundary of the distortion using stacked datasets from Webb, Chandra, and LMA, they found what might be the most unsettling detail of all: the edges were not still. The outline shimmered with microfluctuations, minuscule deviations in curvature that danced across the contour like ripples chasing each other across a pond. They were extraordinarily small, on the order of 1 part in a trillion. But they were real. And they were not static. The fluctuations changed over time. Not randomly, but with a slow periodicity, a rhythm barely detectable yet undeniably present. It was as though the boundary of the anomaly breathed, expanding and contracting by unimaginable small amounts. No known cosmic structure behaved this way. Galaxies moved. Stars pulsed. Black holes accreted matter. But space-time itself did not tremble with such delicate regularity. The team considered more exotic explanations. Some speculated about hidden dimensions predicted by string theory. Perhaps the anomaly marked a region where higher dimensional geometry brushed against our own universe. Others pointed to quantum gravity models where space-time graininess might become large enough to influence photon paths. A few suggested more enigmatic possibilities: a fossil trace of a collapsed wormhole, a relic of symmetry breaking, or an aborted cosmic structure that never fully formed. But none of these theories fit perfectly, and none explained why the anomaly produced an outline rather than a mass-centric distortion. The more the scientists learned, the less they understood. What they did know was simple but profound. Across every wavelength humanity could observe, the same shape emerged. A shadow without mass. A lens without a lens. A distortion neither gravitational nor quantum in the conventional sense, yet etched into both regimes. Its edges flickered with microfluctuations that suggested tension in spacetime itself, tension that behaved like a dormant instability. And all of this, all of the clues taken together, pointed toward a single truth. Whatever the anomaly was, it was not a thing. It was a place. A region where the universe behaved differently, quietly, consistently, and indefinitely. And yet, despite the growing clarity, the heart of the mystery remained untouched. The distortion continued to wait in the dark, unchanged and unchanging. A shadow cast by something that should not exist. And perhaps by something that no longer does. For a time, researchers believed the anomaly was fixed, a silent imprint sealed into the cosmic background like an ancient scar. But new data changed everything. What once appeared still began to drift. Not with the chaotic wandering of a cloud. Not with the inertial glide of a distant object. It moved with a deliberate stillness, as though the universe itself were carrying it on rails unseen. The first hint of motion came from repeat observations by the James Webb Space Telescope. Months after the initial detections, Webb's infrared images revealed a subtle shift. The distortion's outline, once aligned perfectly with a set of background galaxies, had slipped by a fraction of an arcsecond. At first, the change was dismissed as instrumental drift, thermal noise, or a calibration error. But when the images were overlaid with extreme precision, the movement persisted. The shadow's edges had migrated, imperceptibly, consistently. Chandra confirmed it. Its X-ray maps, taken weeks apart, showed the same pattern. The void-like contour no longer occupied the same patch of the high-energy sky. And then ALMA's millimeter-wave interferometry added the final confirmation. Across the cold background, the anomaly had displaced itself with a steadiness difficult to ignore. It was moving, not dissolving, not evolving, but traveling, as if the distortion were an object with no substance, a shape without mass, gliding across intergalactic space. The data teams plotted the drift. The movement was agonizingly slow. At its current measured speed, it would take thousands of years to cross even a fraction of a single parsec. Yet for something that was supposed to be a static warp, any motion at all was seismic. And what made the phenomenon even more unsettling was that the anomaly was not stretching, shrinking, or deforming. It maintained its perfect boundary, its faint curvature, its microfluctuation rhythm. Everywhere it went, the same shape persisted, as though the shadow were a template the universe was reluctantly forced to carry. Scientists attempted to fit the drift into classical mechanics. But nothing fit. The anomaly did not accelerate or decelerate as it passed through regions of denser interstellar medium. Gas clouds, faint though they were, should have left fingerprints, slight distortions in motion, ripples in the boundary, some signal of interaction. Yet the shadow moved through them with complete indifference. It parted nothing. It absorbed nothing. It left no wake. Nearby stars, clusters, and even the diffuse pull of large-scale structure should have affected its trajectory. But the anomaly ignored all gravitational wells. It drifted directly across the weak pull of a nearby galactic filament without deviation. According to the models, even a massless photon would have curved more than this shadow. The universe acted on everything, but not on this. Theorists, once cautiously open-minded, now struggled to explain a phenomenon that behaved as though untethered from the fabric that defined motion itself. If it was some remnant of early universe topology, why would it move at all? If it was a region of altered vacuum energy, why would it remain coherent across millions of kilometers? If it was a relic of cosmic inflation, why was it not fading? The anomaly seemed to follow a trajectory only it understood, a straight line through a curved universe. As more data arrived, the mystery deepened. The drift was constant in speed, neither responding to gravitational gradients nor to momentum conservation. It behaved as though inertia did not apply. In classical terms, it did not carry momentum. It did not resist changes in motion. It simply continued, propelled by a cause not measurable within known physics. Some proposed it might be riding a deeper current in spacetime, a hidden flow predicted in certain models of modified gravity. Others speculated that it might be anchored to a feature beyond the observable universe, its apparent drift merely a projection of larger, unseen motion. But among a small circle of quantum cosmologists, a more unsettling idea took form. If the distortion was not mass, not energy, not curvature, and not a remnant of matter or radiation, then perhaps it was not part of this universe's ontology at all. A boundary, a contact surface, the footprint of something pressing against space-time from the outside. To explore this possibility, researchers conducted a sweep of the surrounding region, monitoring the microfluctuations along its edges with higher time resolution. If something external were influencing the distortion, those fluctuations might reveal the presence of deeper forces. The results were subtle but consistent. The boundary oscillations carried a faint modulation, not random noise, but a pattern, as though the outline were responding to pressure variations in an invisible medium. These modulations did not correspond to any known cosmic process. They were too slow for quantum fluctuations, too smooth for plasma turbulence, and too stable for gravitational waves. To some, it resembled a signature of interaction with a brain-like structure. a hypothetical membrane predicted in certain string theory scenarios. In those models, universes could exist as higher dimensional surfaces, occasionally brushing or distorting one another. Yet the shadow did not behave like a collision site. It did not release energy. It did not deform space-time violently. It simply drifted, quiet and intact. If it was a boundary, it was a passive one. Not an explosion, not a tear, not a rift. More like an imprint left behind by something momentarily touching the universe, then withdrawing, leaving only the ripple. Other theorists drew connections to models of vacuum instability. In those frameworks, the quantum vacuum is not fully stable but metastable, capable of transitioning into a lower energy state under the right conditions. If a region of space temporarily shifted into a different vacuum configuration, it might leave behind a distortion like the shadow, a pocket of altered spacetime that behaves unlike the surrounding universe. But vacuum transitions of this type, predicted by certain standard model parameters, would not drift. They would expand or collapse. They would not travel with such impossible stillness. And so the hypotheses diverged, each more exotic than the last. One possibility became whispered only in cautious intervals. Perhaps the distortion was the footprint of something that passed through, an object, structure, or entity with dimensions incompatible with the observable universe. If such a thing moved through spacetime like a higher dimensional needle threading through fabric, it might leave a trailing boundary, a shadow shaped not by its body but by its brief intersection with a lower dimensional world. But the shape of the anomaly did not resemble a pass-through event. It was too stable, too symmetrical, too consistent. If something touched the universe, it held its shape for far too long. Others suggested it might be the opposite, not the path of something entering, but the trailing mark of something leaving. A footprint pressed into the cosmic floor long after the traveler had disappeared. Yet none of these theories explained what observers saw next. As the anomaly continued its slow drift, it entered a region filled with diffuse hydrogen filaments, remnants of ancient cosmic webs. These filaments, although faint, still possessed enough density to interact with passing energy or mass. Photons scattered, cosmic rays disrupted, gravitational influences shifted, but the shadow interacted with nothing. It moved through the filaments as though passing through the idea of matter rather than matter itself. Sensors detected no absorption, no scattering, no change in drift. It was moving but not through space. It was moving through the metrics that define space, slipping through the cosmic architecture the way a reflection glides across the surface of water. And slowly, a fear began to take shape, not among the public, not among journalists, but among the theorists who understood the implications. If the anomaly was moving, and if its motion obeyed none of the laws governing matter or energy, then it might not be inside spacetime at all. It might be the interface of something adjacent to it, something whose presence warped the universe only where their fabrics brushed. A boundary, not of space, but of spacetime itself. If that were true, then the shadow was not merely drifting. It was revealing that something was moving beyond the horizon of physical law. Something the universe struggled to describe. Something the instruments could detect only by the imprint it left behind. A moving absence, shaped like a footprint walking across the void. As the anomaly continued its silent migration across intergalactic space, the scientific community entered a phase marked not by answers, but by profound and uneasy imagination. For decades, cosmology had operated under a firm pact with the universe, that even its strangest behavior would bow, eventually, to mathematical description. But this shadow, a drifting curvature with no mass, no energy, no thermal signature, broke that pact. If the cosmos offered clues, they came only in faint echoes at the edges of its impossible outline. And so theorists began assembling frameworks, each more daring than the last, yet each grounded in the rigor of established physics. These were not wild guesses. They were extensions of equations already written, possibilities already woven into the deeper layers of theoretical research. The anomaly simply forced these possibilities into the light. 5 leading hypotheses emerged, not as competing answers, but as windows into what the universe might be capable of. Hypothesis 1. a region of negative mass or exotic matter. Some physicists turned to a possibility long debated at the margins of quantum gravity research: negative mass. Negative mass had never been observed, but its existence was not forbidden. In certain solutions to Einstein's field equations, exotic matter with negative energy density could theoretically produce repulsive gravity, a push instead of a pull. It was the same form of hypothetical matter required to stabilize wormholes and warp drives in speculative general relativity models. If the anomaly were a patch of negative mass, its behavior would make a strange kind of sense. Negative mass could reproduce curvature without conventional matter. It could drift without inertia. It could ignore surrounding gravity wells, accelerating in the opposite direction of any force applied. But the details did not fit neatly. A negative mass region should distort surrounding space with characteristic patterns: outward gravitational lensing instead of inward, repulsion instead of attraction. The anomaly, however, behaved like an absence, a soft bending of light akin to a hollowed-out region rather than an outward push. And even exotic matter should radiate, however faintly, through interactions with the quantum vacuum. The anomaly radiated nothing. Still, if confirmed, this hypothesis would rewrite the foundations of physics. It would reveal the first direct evidence of matter beyond the standard model. It would show that space-time could host regions with energy densities unlike anything formed naturally by astrophysical processes. And it would imply that the universe contained far more diversity in its structure than previously imagined, a cosmic zoo of matter types waiting to be uncovered. Yet many researchers hesitated. For negative mass to exist, the universe must harbor symmetries and energy states that remain purely theoretical. The anomaly offered no proof, only suggestion. Hypothesis 2. A shadow cast from another dimension. The second hypothesis reached deeper into geometry itself. In models inspired by string theory and higher dimensional physics, the universe may not be a single, isolated stage, but one layer in a larger multidimensional structure. In these frameworks, gravity is not confined to the familiar four dimensions. It leaks. It bleeds. It spreads through higher dimensional space known as the bulk. If something massive moved through the bulk, something not part of the observable universe, it could distort the geometry of spacetime where its influence brushed against ours. The result would be a projection, a higher dimensional shadow cast into the three-dimensional cosmic fabric. The drifting anomaly, with its perfect boundary and massless curvature, fit this description disturbingly well. A higher dimensional object could cast gravitational influence without being physically present. It would not radiate. It would not absorb. It would not interact with ordinary matter. Its motion would be governed by rules outside our spacetime, appearing to us as a slow, deliberate drift. Some cosmologists imagined a massive four-dimensional structure passing close to our universe's brain, a silent silhouette brushing against the surface of spacetime. Others proposed that the anomaly might not be the object at all, but merely the cross-section where a higher dimensional curvature intersected with three-dimensional geometry. If true, this would mark the first direct evidence of the multiverse, not as a philosophical concept, but as a physical reality. It would mean the cosmos was not a lone island, but part of a vast archipelago of dimensional layers. But such proposals came with staggering implications. If the anomaly represented a shadow from another dimension, then its drift was not movement through space, but the motion of the universe itself sliding along unseen geometries. The cosmos, it seemed, might be brushing shoulders with something larger. Hypothesis 3. A fracture or bubble in the vacuum field. Other theorists looked inward, not to dimensions beyond space, but to the quantum vacuum itself. According to quantum field theory, empty space is not empty. It swarms with ghost-like fluctuations, virtual particles, and fields humming in constant activity. Beneath this restless surface lies a deeper structure, the vacuum energy state. Some physicists believe the universe's vacuum may not be in its lowest possible state. Could be metastable, temporarily stable, but not permanent. If a region of space fell into a lower energy configuration, it would create a bubble of altered vacuum. This bubble would have radically different physics inside it. Different particle properties, different constants, perhaps even different laws. If the anomaly were such a bubble, it would explain its massless curvature and lack of radiation. A vacuum domain shift could warp spacetime without absorbing or emitting energy. And if the bubble's interior possessed slightly different vacuum energy, the boundary would act as a tensioned membrane, consistent with the microfluctuations observed along its edges. But this explanation carried a darker implication. In many models, a bubble of true vacuum would expand at near light speed, consuming the universe. The fact that the anomaly drifted calmly suggested it was not true vacuum, but something weaker, an incomplete transition, a local fracture that never fully ignited. If this hypothesis were correct, the anomaly might be the first recorded evidence of vacuum instability in the observable universe. A sign that the cosmic vacuum is not static, but evolving. A reminder that the universe, at its deepest level, may be more fragile than previously believed. Hypothesis 4. A gravitational echo of a vanished object. Some researchers proposed a more haunting idea, one that did not require new particles or extra dimensions. Throughout the universe, objects come and go. Stars collapse. Neutron stars merge. Black holes evaporate through Hawking radiation, releasing a faint whisper of quantum energy into the void. If a massive structure had once existed where the anomaly now drifted, perhaps its disappearance left a residual imprint, a gravitational echo. This echo would not be matter. It would not be energy. It would be curvature, the lingering deformation of spacetime that had not yet relaxed into equilibrium. The shadow could be the afterimage of something that had vanished so completely that only its gravitational footprint remained. In such a scenario, the drift might be the relaxation process itself, curvature returning to balance, sliding across spacetime like ripples on a pond. Yet there were problems. Gravitational relaxation occurs quickly on cosmic timescales. Even the largest mergers settle within millions, not billions, of years. The anomaly, by contrast, persisted with unnatural stability. It held its shape as though preserved by something preventing its decay. If it was an echo, then whatever created it was unlike any event ever recorded. Perhaps a black hole collapse through Hawking evaporation. Perhaps a primordial object that winked out of existence due to quantum instability. Perhaps something even older, a relic from the first seconds after the Big Bang. If true, the anomaly could be a message from the universe's deep past, preserved not in light, but in the curvature beneath it. Hypothesis 5. A boundary wall from early universe inflation. The final leading framework looked back to the earliest moment of cosmic history. During inflation, the universe expanded faster than the speed of light, smoothing space and stretching microscopic fluctuations to cosmic scales. In some inflationary models, this rapid expansion left behind domain walls, thin boundaries separating regions that cooled at slightly different rates or settled into different vacuum states. Most of these walls would have collapsed billions of years ago. But if one survived, weakened, thinned, nearly dissolved, it might persist today as a faint curvature with no mass, drifting slowly as the universe expands. The anomaly's perfect boundary and soft imprint match these predictions. A relic inflationary wall would not radiate. It would not interact. It would exist as a fossil structure, older than galaxies, older than stars, older than light itself. If this were true, then the anomaly was not a visitor. It was a survivor. A message from before the universe was fully born. A fragment of the cosmic blueprint left behind as inflation carved spacetime into form. In the end, none of the theories provided a complete answer. Each opened a door into a different vision of the cosmos. A universe of exotic matter, hidden dimensions, unstable vacuums, gravitational ghosts, or ancient boundaries. Each forced physicists to confront possibilities once considered purely theoretical. But if one thing became clear, it was this. The anomaly did not merely challenge scientific understanding. It expanded it. It pushed the limits of what the universe might contain. It whispered that the cosmos was larger, stranger, and far more layered than humanity had dared to imagine. Across the scientific world, an unusual sense of alignment has begun to form, A quiet convergence of instruments, observatories, and minds, all turning toward the same enigmatic presence drifting through the cosmic dark. The shadow, as it has come to be called, moves without radiance, without mass in any familiar form, yet with a mathematical sharpness that refuses to be ignored. To understand it, scientists have gathered the finest tools humanity has ever placed against the void, each one listening for a whisper, a tremor, a deviation that might reveal what laws of nature still lie hidden. The effort begins with the most delicate ears humanity possesses, the global network of gravitational wave detectors. Facilities like LIGO in the United States, Virgo in Italy, and Kagra deep beneath the mountains of Japan were designed to capture ripples in space-time itself, faint distortions first predicted by Einstein and confirmed only in 2015. These instruments measure shifts thousands of times smaller than a proton's width, tracing the dying spins of black holes or neutron star collisions billions of light-years away. Now, their sensitivity is being used for something far stranger. Researchers have begun searching for gravitational fluctuations that do not match the signatures of known astrophysical events. Instead of the characteristic chirp of merging objects, they look for slow, drifting patterns, subtle oscillations that may rise and fall as the shadow moves across the sky. These patterns would not imply mass in the conventional sense, but rather the warping of space-time by something more elusive, perhaps a defect, a boundary, or a region where vacuum energy behaves unlike anything seen before. So far, the detectors have reported hints, small deviations, barely above the noise. None are decisive, yet none can be dismissed. For the first time, gravitational wave science is being asked not just to observe the violent cosmos, but to listen for the quiet geometry of reality itself. Parallel to this effort, a new generation of theoretical missions is taking shape in design studios and simulation labs. At the center of these discussions is a bold proposal, a dedicated deep space probe whose sole purpose would be to intercept the shadow directly. Such a craft would travel far beyond Earth's magnetic cocoon, carrying instruments designed to measure how the vacuum behaves at the shadow's boundary. To approach such an object, if it can be called an object, requires a radically different philosophy of exploration. Traditional spacecraft are built to observe light, particle flux, dust, or gravitational influences. But the shadow emits no light. It sheds no particles. Its gravitational fingerprint, if it exists, is so faint that only the largest observatories barely notice it. So engineers propose something unprecedented, a suite of quantum sensors capable of detecting minuscule fluctuations in the vacuum field itself. These sensors rely on quantum coherence, holding atoms or photons in superposition to observe changes in fundamental fields that classical instruments would overlook. If the shadow represents a boundary in vacuum energy, or a region where space-time curvature shifts subtly, these devices might record phase shifts or decoherence patterns as the probe drifts across its edge. It would be one of the most delicate measurements ever attempted in space, a direct test of the vacuum, the very fabric from which matter and light emerge. For now, the mission remains in study phase. But the momentum behind it is growing. Space agencies across continents have expressed interest, and an international task force has begun drafting the early requirements. The shadow is simply too unusual, too precise, to ignore. Behind these engineering efforts, another frontier has opened, one that takes place not in the vacuum of space but in the abstract realm of computation. Quantum computers, still in their infancy, are being asked to model what classical supercomputers struggle to represent: exotic defects in space-time predicted by certain quantum gravity theories. These simulations attempt to capture how the vacuum behaves under extreme conditions, such as the presence of negative energy density or topological boundaries left over from the earliest moments after the Big Bang. Classical computers can solve equations for smooth space-time, for matter fields, for gravitational curvature. But exotic phenomena, wormholes, cosmic strings, vacuum bubbles, involve quantum rules that are deeply entangled and non-local. Quantum processors, even with their limited qubit counts, can mimic some of these entanglements, generating early models of how a space-time fracture might move, how it might distort the vacuum around it, and what signals it might leave for observers millions of years later. Most simulations remain crude. The shadows they produce lack the clean boundaries seen in astronomical data. But occasionally, during test runs, a pattern emerges that resembles the observations. A smooth, persistent void-like region, not caused by absence of matter but by an alteration of the vacuum itself. It is enough to keep theorists fascinated, enough to keep supercomputers cycling late into the night. Yet beyond tools and theories, there is something more profound at work, a rare moment of global scientific unity. Teams who once competed for telescope time now share data. Laboratories that once guarded their models now publish them freely, hoping someone, somewhere, will recognize the missing piece. The mystery is too large, too fundamental, for territorial science. Radio observatories adjust their schedules to monitor the shadow's trajectory. High-energy particle physicists study how vacuum fluctuations might mimic its behavior. Cosmologists revisit inflation models, wondering whether primordial boundaries might drift across the universe like ghosts of ancient expansion. Every discipline touches the mystery from a different angle, and each one contributes a fragment of understanding. The collaboration is urgent, though no threat has been identified. The urgency comes from awe, from the realization that the shadow is not merely a patch of darkness but a window into deep physics. If its nature can be understood, the universe may reveal something it has hidden since its beginning, a clue that rewrites assumptions about space-time, gravity, or quantum fields. Satellite networks observe its slow drift with increasing precision. Mapping teams have begun producing high-resolution models of its shape, its edges, its subtle interactions with background radiation. Though it leaves no visible trace on starlight, small distortions in the cosmic microwave background appear near its boundary, faint, smooth depressions in temperature that suggest the vacuum behaves differently there. If confirmed, these distortions could be evidence of vacuum defects or exotic energy configurations predicted by early universe theory. Even neutrino detectors, vast underground chambers of water or ice, have been enlisted in the effort. Researchers probe their data for anomalies, hoping that the shadow interacts faintly with neutrinos, the universe's most elusive particles. So far, the results are inconclusive. But the search continues. In every corner of science, the same feeling spreads. This phenomenon is not noise, not illusion, not equipment failure. It is something real, something structured, something with rules, waiting to be decoded. And so a picture begins to form, not yet complete, but sharper than before. A network of instruments listens to space-time. Engineers craft probes meant to touch the vacuum. Quantum computers simulate the unthinkable. Theories rise and fall with each new measurement. And across countries and cultures, scientists speak with a single voice. This is not merely a discovery. It is an invitation. An invitation to understand the universe not as a finished masterpiece, but as a living, shifting architecture with secrets still unfolding in the quiet dark. The shadow moves onward, silent, indifferent, yet strangely precise, drawing behind it the gaze of a species just beginning to understand the scale of the mysteries that surround it. The universe, for as long as humanity has looked upward, has been a landscape of shadows and light, of absence and presence, of things revealed and things withheld. Night after night, across millennia, civilizations have gazed at the stars and found in their darkness a reflection of human fear, human longing, human wonder. Every shadow cast by a moon, a planet, a cloud of dust, or a distant star was, in some sense, proof of something tangible, an echo of matter, a consequence of light obstructed. Even the void itself, the blackness between galaxies, felt filled with invisible weight, a canvas upon which the universe painted its known laws. Shadows were always traces, always evidence, always relational. They pointed to something that existed. And now, for the first time, the cosmos has presented a shadow without a source. It is a curvature without mass, a bending of light with nothing to bend it, a silence in the fabric of space-time that cannot be explained by the physics that have guided centuries of exploration. The anomaly drifts through the intergalactic void like a ghost that refuses to acknowledge its own existence. It is a presence defined entirely by absence, a boundary traced in the negative, a message written in the geometry of nothing. To witness this is to confront the limits of perception itself. Humanity evolved to perceive a world defined by tangible interactions. A stone falls because mass attracts mass. Light travels along predictable paths, heat emanates from matter, energy cannot be created or destroyed. These are the rules of engagement with reality that have allowed civilization to survive, to measure, to predict. And yet here is a phenomenon that respects none of these rules. A subtle insistence that the universe is not bound by the simplicity of human intuition. It suggests that reality may be composed of layers that the senses cannot detect, that the fundamental scaffolding of existence may extend into domains where mass and energy, space and time, are mere local approximations of deeper truths. There is a profound poetry in this realization. Throughout history, humans have feared the dark, yet the darkness has always been at least partially knowable, a veil over something tangible. Here, the shadow is nothing tangible. It is not a veil, but a revelation of absence. And yet, it is as if the universe has deliberately chosen to make this absence visible. A trace, not of light or matter, but of possibility. Perhaps it is a cosmic whisper, reminding us that the universe is not simply a stage upon which events unfold according to our calculations, but a living architecture whose contours extend beyond the grasp of the mind. Philosophers and physicists alike feel the weight of such a shadow. It calls into question the very act of observation. If a curvature can exist with no cause, if a shadow can drift without a source, then the role of the observer is fundamentally redefined. The universe may contain phenomena that do not interact with the tools we have built, that leave no radiation, no particles, no measurable energy. The boundaries of knowledge, once thought to be defined by the sharp edges of mathematics and experiment, become porous. Reality itself becomes an invitation to imagine, constrained not by what is seen but by what might be. The shadow also forces an emotional reckoning. It is not threatening in the conventional sense, it does not radiate danger, nor does it seek to annihilate. Its presence is gentle, almost deliberate, yet its implications are unsettling. Humans have long sought to categorize, to name, to anchor their understanding in observable patterns. Here, the universe has denied that anchoring. The anomaly is a reminder that comprehension is always provisional, that every theory, every equation, every carefully constructed model is a lens rather than a mirror. And within that lens, a shadow without a source appears like a crack in perception itself, a fissure where certainty slips into wonder, where the known gives way to possibility. Some have described it as a moment of humility on a cosmic scale. To behold this drifting void is to recognize that no matter how far observation reaches, no matter how refined instruments become, some truths may lie just beyond detection, just beyond the architecture of sensory perception, waiting in forms that the human mind has yet to imagine. The shadow challenges the anthropocentric notion that the universe exists to be understood, that light, matter, and energy are the only currencies of reality. It suggests instead that absence, subtlety, and curvature itself may be fundamental, that the cosmos might be more nuanced, more layered, and more ineffable than even our boldest theories allow. And yet, there is a strange beauty in this unknowability. In the quiet drift of the shadow, there is a rhythm, a poetry, a reminder that the cosmos does not exist merely to serve human understanding, but to exist on its own terms. The anomaly traces a path across space as elegantly as any comet or galaxy, yet it does so without consuming energy, without interacting with the matter around it. Its very existence is a meditation on the potential of reality, a subtle suggestion that the universe is richer, stranger, and more mysterious than the story of stars, planets, and galaxies alone can convey. In this sense, the shadow becomes more than a scientific puzzle. It becomes a symbol, a visual metaphor for the boundaries of perception, the humility of knowledge, and the possibility that existence itself contains dimensions, rules, or phenomena that remain entirely hidden from human senses. It is both a challenge and a gift, a challenge to the certainty of physics, and a gift of wonder, urging us to expand the imagination as much as the telescope, to explore not only the universe we see, but the universe that might exist beyond it. Some have whispered that the shadow could be the first tangible hint of a deeper architecture of reality, a higher dimensional layer, a relic of early inflation, a subtle fracture in the vacuum of space. Others say it is simply a reminder that the universe does not owe explanation, that it can reveal without showing, can gesture without disclosing, can exist in ways that defy human expectation. Whatever its nature, the shadow has already begun to transform the human approach to cosmology, reminding us that scientific curiosity is inseparable from philosophical reflection, and that the pursuit of understanding is inseparable from the confrontation with mystery. The more we attempt to categorize it, to measure it, to simulate it, the more it teaches us about the limitations of knowledge and the expansiveness of possibility. The shadow asks us to recognize that the universe may be vaster than the sum of its observable contents, more intricate than the equations that describe stars and galaxies, more profound than the instruments that scan the skies. It beckons us to contemplate not only what is, but what could be, the invisible, the improbable, the unmeasured, and perhaps the fundamentally unknowable. And in the end, there is a quiet acceptance, a cinematic, almost meditative recognition that the shadow is not something to conquer or categorize. It is something to behold, to ponder, to let expand the mind beyond its usual constraints. It drifts through space without disturbance, without intent, yet it leaves a lasting imprint on those who study it, a reminder that the universe is not merely the sum of its lights and matter, but also the negative spaces, the silent curvatures, the shadows that speak without source. As humanity continues to build instruments, run simulations, and refine theories, the shadow remains patient and distant. It does not hurry, it does not falter, it does not vanish. It drifts across intergalactic darkness like a reminder that reality is more than what we can see, and that some truths are subtle, profound, and impossible to grasp fully. It invites the human mind to contemplate infinity, absence, and the possibility that beyond the limits of perception lies a universe larger, stranger, and more unknowable than any story humanity has ever told. In the presence of this shadow, science meets philosophy, mathematics meets wonder, and observation meets contemplation. And perhaps, in its silent drift, it offers a quiet consolation, that in acknowledging what we cannot see, we begin to understand the true scale of what exists, the immensity of the cosmos, and the humility with which we must approach its mysteries. The shadow continues its journey, unmarked by time, unobserved by anything but our instruments, yet impossible to ignore. It is a silhouette of absence, a curvature without cause, a reminder that the universe may be more intricate, layered, and profound than any story, theory, or imagination has ever conceived. And for the first time, humanity confronts a darkness that is not merely the absence of light, but the presence of something wholly unknown, a cosmic shadow whose existence itself asks the most profound questions about the nature of reality. In that reflection, there is awe. In that contemplation, there is humility. And in that moment, humanity recognizes that the cosmos is vast, mysterious, and beautiful beyond measure, and that the shadow is perhaps only the first whisper of what lies beyond the edge of understanding.